Okay, number 4. I won't read the whole question, but I'll explain what we have here. Here we've got a mass, small m, tied with a string, capital L is the length of the string, and this mass is made to turn around this pole. We've got tension in the upper string is called T1, tension in the lower string is called T2. We've got the angle here, theta. Distance from top to bottom is small d. So to the middle part it will be d on 2. I've drawn already the diagram here. Exactly what we have over there. And before working out the problem, I need to take the top part of the triangle to get what is sine and cosine theta. Sine theta is opposite on hypotenuse, so it will be d on 2 over L, and that is equal to d over 2L when you arrange it. Cos theta is adjacent on hypotenuse, so it will be r on L. R is this distance over here, which is the radius of rotation of the ball as it's going to go in a circle. Okay, it's going to rotate like that. Now, also, we need the forces to be all vertical and horizontal. T1 and T2 are diagonal. We need to use the components. So for T1, I will do this. And we'll get the component here, T1 sine theta. And over here, we get T1 cos theta. At the bottom, we've got T2. Here, we'll have T2 sine theta. And over here, we'll get T2 cosine theta. To prove the first equation, we have to consider vertical forces, and I can say forces to the top are equal to forces at the bottom. So we'll write down this equation. T1 sine theta equals T2 sine theta together with mg. That is for the first equation. I will divide everything by mg. Everything by sine theta. And we'll see that sine theta cancels here and also here. Left hand side becomes only T1. Right hand side will get T2 plus mg over sine theta, but we know that sine theta is d on 2L, so instead of sine theta, I'll write down d over 2L. 2L is divided here at the bottom, so we'll take it to the top to become multiplied. So this part will be mg over d, but the 2L goes to the top, which I can write like that. And over here remains T1 and T2. Part A tells us to get an equation for T2, subject of the formula. So the final part will be T2 equals T1 minus all of that goes to the other side to become 2mgl over d. Okay, T2 equals T1 minus 2mgl over d. For the second part of the problem, we need to get an equation for omega. This time we're going to consider the forces to the center, which are T1 cos theta and T2 sin theta. Since the mass is doing circular motion, those forces are equivalent to the centripetal force. So we can say that T1 cos theta plus T2 cos theta equals mr omega squared. I'm using mr omega squared for centripetal force because I need an equation for omega and not for velocity. So this over here is the centripetal force, mr omega squared. Left hand side we can see that cos theta is constant, is common, so we'll take it out in the brackets. So here I will have T1 plus T2 cos theta in brackets equals mr omega squared. We know that cos theta is equal to r on L, so instead of cos theta, I'll write down r on L equals mr omega squared. Radius is common on both sides, so radius cancels. Mass will take it to the bottom, and that will be equal to omega squared. So here we will get T1 plus T2 and times 1 over ml equals omega squared, but instead of squared, I'll get square root in this part over here. And to continue now, what I need to do is I need to get a substitute T2. Instead of T2, I'll put T1 minus 2mgl on D, because we've already proven that. So for omega, I can get T1 plus, and instead of T2, I'll write down T1 minus 2mgl over D. And all of that is equal to omega. We can say that, see that we've got T1 and T2 common, so we add them up over there. That will be twice T1 minus twice mgl on D. I forgot the times 1 on ml. Okay, times 1 on ml here is equal to omega. And finally, 2 is the only thing that is common. We'll take it outside. So it will be T1 minus mgl on D times 2 on ml equals omega, which is what we needed to prove in this part of the problem. Finally, for part C, we are told that during rotation, the lower ring slips upwards so the distance small d decreases. Explain the effect this has on frequency of rotation of the sphere. To answer this question, we have to look at the previous equation, and we have to say that what's going to happen to omega if distance d decreases. And as we can see, if small d decreases, we can write it down. If d decreases, mgl on d will increase, because if the denominator decreases, all the value is going to increase. This means that T1 minus mgl on d, if this value is going to increase, it will decrease. So T1 minus mgl on d is going to decrease. And if this value decreases, omega decreases. So we can say, so omega decreases, or it will rotate with a smaller angular velocity.